out the matrix of the linear transformation. First linear transformation is R, which is from R2 to R2, which reflects vectors with respect to the line y equal to x tan theta. Okay, so let's first do the initial part. So first we'll show that HU is indeed an orthogonal matrix. For that we need to compute HU into HU transpose. That gives us this HU into HU transpose. So here we can see we apply transpose. In the second part it gives us I transpose minus 2 UUT whole transpose, which is U transpose transpose into U transpose. But we know that taking transpose 2 times is the original vector itself. So we get this. And then we go on to multiply. We multiply it manually to get this. Okay. And once we get this, we have your minus 2 contributes to minus 4 U transpose. And this gives us 4 U transpose. And please note here that U is a vector in Rn, which is not arbitrary vector. It turns out to be a unit vector, because of which U into U transpose is exactly equal to 1. It gives us this. These two terms go away to give us identity. Okay? And similarly, you can even show that HU transpose into HU, which is more or less the same calculation. It will turn out to be identity. Therefore, HU is an orthogonal matrix. Okay? Next, this reason is written over here. U transpose U is equals to 1. Therefore, we get this. We get rid of these two products. Next, we have to calculate HU, how it acts upon alpha U. So for any alpha, arbitrary alpha in R, what does HU do to this alpha U? So HU is just I minus 2 U transpose times alpha U. That is equal to alpha U minus 2 alpha U transpose into U. Okay? That is again equal to, again we use the fact again and again that U transpose into U is equal to 1, which gives us alpha U minus 2 alpha U, which is equal to minus alpha U. Okay? So we have seen how does HU act on alpha U. So action of HU on alpha U is just minus alpha U. Okay? Next, we have to find out how does HU act on the vectors which are perpendicular to LU. Okay? So, perpendicular to LU, which means that V is perpendicular to U. So HU of V would then be this. Then we expand. Identity operated on V is just V, and this gives us 2U transpose V. Okay. Again, we use the fact that U transpose U is equal to 1, which gives this to be equal to, okay. Oh, no, I'm sorry. So here it should be V minus 2 U transpose V. So here actually we are taking V to be perpendicular to U. Okay, because of which this inner product, what is inner product of U and V? It is U transpose into V, right? This turns out to be 0. And therefore this expression does not contribute at all. This term in this expression does not contribute at all. Okay, so we get V minus 2 U transpose V. This term is 0, so therefore we get this V. So now let's see what this means geometrically. So geometrically we see that HU is the matrix of the linear transformation which reflects the space with respect to the hyperplane perpendicular to U. Okay? So U is a unit vector. HU is the matrix of the linear transformation which reflects the space with respect to a hyperplane perpendicular to U. You can easily visualize this in R2 at least. Okay, yeah. So next, let's move on to use HU in order to compute the linear transformations. Okay, so we have to find out the matrix of linear transformation R, which reflects vectors with respect to the line y equal to x tan x. So there's a line y equal to x tan x. So we, in order to calculate this, we need to find out HU, because just now we have seen what is the geometric interpretation of HU. Use any unit vector perpendicular to the line y equal to x tan theta. So we pick up any unit vector perpendicular to this line So we can put u equal to sine theta minus cos theta. We are picking up a column vector in R2, which is a unit vector, and this unit vector is going to be perpendicular to our line along which we want to reflect, with respect to which we want to reflect. Huh? So then we have this calculation. So R will exactly be equal to HU, and HU, what is HU? So HU is just I minus 2U U transpose. So I minus 2U, so I've written U over here, and then U transpose here. Then we can see that I minus 2U, just multiply these two terms to get matrix, 2 cross 2 matrix, and then I minus 2 times that matrix will give you this. And then it is always better to put it in a compact form. So we see here that we use the formula of sine 2 theta and cos 2 theta to describe R in terms of trigonometric functions of 2 theta. 2 theta. So this gives us the vector R. So we've seen here that how HU is being used in calculating this linear transformation R. This is the reflection along this line. So next is a similar thing that we want to do. We want to compute the linear transformation T from R3 to R3, which reflects the vectors with respect to this plane. So now we are in R3, so we are interested in finding out the transformation which reflects with respect to this plane. Here again we'll be using HU because we have proved the formula for HU in arbitrary dimension, in any Rn, in any Euclidean space Rn. So it is enough to find HU again, where U is any unit vector which is perpendicular to the plane x plus y plus z is equal to 0. So we choose U to be equal to this. Then HU will be equal to I minus 2 U transpose. This is again same calculation, same basic calculation that we need to do. I minus 2 by 3, this times this, so it gives us, so again we multiply these two matrices. Now this will be a 3 cross 3 matrix. And then we see that we get this matrix. So HU is exactly equal to T. Okay, so HU is exactly equal to T. So HU is the matrix that we are getting out here. Any doubts? We just have two more problems left. So please, if you have any doubt, please let me know in the chat box. Soumya, can you understand? Are you okay till problem 6?
Yes, yes.
Yeah. Okay. So this gives us, yeah. So the problem does not stop here. So we have to calculate the linear transformation T. So we just calculate T, A comma B comma C. That will be, so the matrix associated to T is here. That is HU. So for finding out T, we just multiply this HU with the vector A, B, and C to get the linear transformation. Next is problem 7. Problem 7 says let V equal to C01, which is equal to the collection set of all continuous functions from 01 to R, with inner product given by Fg is equal to integral 0 to pi Ft Gt dt. Let xn t equal to cos n t for all n equal to 0, 1, 2, and so on. So this is the space, and here the inner product defined is in this way. Now we have to prove that the functions y0, y1, y2, so on, given by this, form an orthonormal set spanning the same subspace as x0, xi. Okay. So first we note that y0 t is exactly equal to 1 by root pi x naught. It is just by mere calculation. Cos 0 is 1, so we get this. And y and t. Okay, so y and t is exactly equal to square root of 2 by pi xn t for all n greater than equal to 1. Okay, therefore, the spans of these two will exactly be the same. The space which is spanned by the xi's and the space that is spanned by yi's, these two remain the same because we have shown that yi's can be written as some constant term into xi, and similarly, if we take root pi to that side, the x0 can be written, for example, as square root of pi into y0. So we are able to even write x0 as a linear combination of y0, and similarly here, we will be able to write xnt as square root of pi by 2 into int. So therefore, we have written xi in terms of linear combination of yi and vice versa. Therefore, these two are the same space. Okay. Next, it remains to show that these are orthonormal. So let's move on to do that. So we have already seen earlier in tutorial 3 that these vectors are linearly independent. We had integrated it with cos and taken limits 0 to 2 pi to see that the set turns out to be linearly independent. No? So next we'll just show that the inner product of y0 that is equal to 1, and for yi, yj, where I is not equal to j, the inner product is 0. So for yn and p, we see that for all n from 0, 1, 2, so on, y0, what does it give? The inner product, it was defined to be integral 0 to pi, 1 by pi d. Okay, so the inner product is fp gt. So here f and g both are equal to y0, which is equal to 1 by root pi. Therefore, we get this. Okay. Next, yn. So we need to show that they have the norm of int for all n from 0 onwards is equal to 1. So for computing the norm, we compute the inner product first. So we compute inner product of yn, that is integral 0 to pi 2 by pi cos square nt dt. That gives us this, which will be equal to 1. Yeah? So therefore it is orthonormal. And one more thing is that why is it following that inner product of yi comma yj is equal to 0? That is because they are linearly independent. The set is linearly independent. So therefore we have shown that they are orthonormal. Next, we have the last problem in this sequence. So here we have the real vector space C02 with inner product defined to be this way, integral 0 to 2 fx gx dx. Let fx be equal to e to the x. So we have to now show that the constant polynomial g nearest to e to the x is equal to this. So we know the formula how to calculate the constant polynomial which is nearest to a function. So it is given by this, right? Pf1. So f is the function of which we have to find the constant polynomial. So it is inner product of f1 upon norm 1 square. Okay? So we can see here that the inner product is just defined in this way. So we just plug in that. Yeah, so inner product of f and 1 will just be f is e raised to x. So the numerator will just be integral from 0 to 2 e to the x dx. And the denominator will be integral 0 to 2 fx dx. Both are equal to 1 because we are computing one term. Okay, fx dx equal to 1 because we are taking inner product of 1. So here, and this directly gives us the integral value. So it is equal to 1 by 2 into e square minus 1. So this is exactly the constant polynomial which is nearest to e raised to x.